My name is Janaka Ranasinghesagara. So I'm going to talk about modeling focus beam propagation in scattering media. So my goal is to talk about why we need computational model of focus beam propagation in scattering media. And then I'm going to talk about some principles and concepts we need to model focus beam propagation. And then finally, I'm going to talk about a model we developed over here. I like to pull this chart back. In this one, if you look at this depth, in microscopy techniques belongs to the depth smaller than 1 millimeter. And especially when you use this log scale, you can expand that one because so we always use log scale to highlight something. So in this case, even though this depth region is belong to a small scale, there are a lot of microscopy techniques in this region. So when depths, when this length scale is small, we have to consider electromagnetic waves for modeling. But when depth scale is bigger, we can consider light as neutral particles and use RT or Monte Carlo simulation for that region. So I'm going to concentrate on electromagnetic wave for this modeling. And first, first, we are going to look at focus beam propagation in free space. So there's no scatterers in this case. When we have a beam, it's not, okay. Do you have another? Oh, okay. So, okay. So here we get a focus beam, and we can use analytical solution to model that one. And when you model using analytical solution, we can get different slices. We get a uniform propagation of this electromagnetic wave. And there's a high intensity spot at the center. Once we get a cross section, it's going to look like that. This is the amplitude. And then we can also plot the phase of that one using this analytical solution. Let's look at this analytical solution in detail.
The pointer is working.
Oh, it's working. Okay. So, because we want to look at this one, we want to see how we model light propagation when there is no scatterer. So, in this case, the plane wave incident upon this lens, and then spherical wave is propagating toward the focus. And in ideal case, we can model this lens as a spherical cap. This is a geometrical representation of a lens. This is how this analytical solution was developed. We consider this lens as a spherical cap and then use electric field and propagate toward the focus. And this is the equation they use. I'm going to come back to this equation later because there are some components like electric field, phase in this equation. I'm going to explain this one later after explaining fundamentals. So the main question ahead of us is to model this case, how we model focus beam propagation in a scattering media. So we have scatterers, like a couple of scatterers like this, or we have this kind of a thick tissue, and we have different kind of scatterers. And this problem is a complex problem, and it's a very hard problem. And finding a solution to this problem is really hard. So this is what we are trying to achieve. But we have to start from simple case, and then we have to go from there. So in this afternoon lab, you are going to do a simulation, something similar to this one, and see how the focus beam is distorted by different scatterers, different size of scatterers, and then maybe you are able to think about how we can go forward from there, how we can model a bigger problem. First thing is to look at what are the existing models to do focus beam propagation. One technique is using Monte Carlo simulation. Even though the Monte Carlo simulation is a solution to RTE and it is using neutral particles, people are using this. So in this case, the photons are starting from the surface and propagate toward the center. And when we use Monte Carlo simulation, we ignore the wave nature of light. So we don't consider light diffraction or interference in this case. So and also we consider far field phase function. That means we get the scattering field distribution in far field and apply that information for these calculations. And we consider these scatterers are randomly distributed. So the results we get is giving the mean behavior of scatterers. We have scatterers at specific places, but when we apply Monte Carlo simulation, we get the mean behavior. And to get a solution, we require a large number of photons. So we have some deficiencies here. We can get some kind of an approximate solution, but that is not the actual thing what we need. So in opposite to that one, we can use finite difference time domain solution for Maxwell's equation. So in finite difference time domain, what we do is we consider a volume, and then we represent that volume with small voxels. And so once we define that one, we can start to propagate waves from the bottom. If we start from bottom, then we can propagate waves and get the output. But to get the accurate results, we need to have a small size of voxels, especially to get a solution without any errors, we need to have a size smaller than 1/20th of the wavelength. So that is a quite small length. So normally we are talking about wavelength around 600, 700 or in that range. So 1/20th of that is going to be 25 to 50 micron nanometers, nanometers. And so the size of voxel has to be so small. Then we need large number of voxels to cover this volume, like 15 by 15 by 50. We need large number of volume. To do this kind of simulation, we need big computers over the supercomputers and large memory, and the time we require to do this kind of simulation is like 500 hours or 3 weeks, something like 3 weeks. And other than that, when we represent spherical particles with voxels, there are some staircase errors like this one. So we cannot accurately represent the spherical particle with voxels. So we have those kind of errors in finite difference time burning. But still we can represent the light as electromagnetic wave, and we can consider all the interference diffraction in this solution. The problem is time. So now I'm going to go back and talk about key concept, equations, and properties. The first thing is light is an electromagnetic wave. It has an electric field and a magnetic field. They are mutually orthogonal to each other, and the propagating distance is perpendicular to electric field and magnetic field. And the wavelength is the distance between two peaks. And I think in earlier lecture we talked about Maxwell's equations. So Maxwell equations are the foundation for electromagnetic wave propagation. We can use Maxwell's equation to describe electromagnetic waves. It is a theoretical foundation, so it can model wave interference, diffraction, and polarization. If you look at this Maxwell's equation, I'm going to briefly explain Maxwell's equation. So in the first one, what it says is if there's a change in magnetic field, that will generate the electric field. So when we take a closed volume, the change in magnetic field will generate electric field. The second one is when there's a change in electric field, that will generate a magnetic field. In addition, when there's a current density, that will also generate a magnetic field. The third one is when we take a closed loop, the electric field is equal to the charge density. And when we take a closed loop, the total magnetic field is going to be zero because magnetic lines are circulating, so there's no net magnetic field. Okay, so if we consider this equation, we don't see any relationship between this and light wave. So we want to use these equations to get a relationship between this one and light wave. So we can come up with a wave equation. So for that one, I consider free space. When there's free space, no flow of current. So this J is going to be zero. Then we can combine these two equations and obtain the wave equation. So this wave equation can explain the wave propagation in free space. So that is why we are saying, okay, we use Maxwell equation for electromagnetic waves. So this is how we can apply Maxwell's equation to get into wave equation. Then once we have wave equation, we need to find a solution for the wave equation. That solution will satisfy this wave equation. One solution is this plane wave solution. So this one has E naught, that is the amplitude, that's the maximum value, and it has a cosine function. So this is a cosine function and also sine function. Both of them are solution to wave equation and called plane wave solution. And once we consider that plane wave, this is known as the amplitude, E naught, or the maximum value is known as amplitude. And the argument within the cosine function is known as the phase. And then we can obtain the intensity by cross product of electric field and magnetic field. Then when we have large number of waves, when we consider the phase of each wave and combine them, that will generate a plane. For plane wave, it will generate a flat plane, and it's called a plane wave front. And okay, so this is the plane wave equation, E naught cos omega t. If we use only this plane wave equation and substitute values, let's say E naught equals 1, then cos this kz omega minus omega t is 0.5, this will end up with a value of 0.5 or certain value. It doesn't represent, it doesn't give the amplitude and phase information. So to retain the amplitude and phase information, what we do is we represent this wave as a complex vector. So we introduce a complex part. This is a complex number. Complex number has a real part and imaginary part. We use I in front of imaginary part here. And so only real part gives an exact value, and then the imaginary part carry the information of the phase. this is how we do when we have this complex representation. We calculate the amplitude by getting the square root of real value and square root of imaginary value and get the square root of that. We can obtain the amplitude, and then we can get the ratio of imaginary and real value and get the arctan of that. That will give the phase. So this is why we represent the wave using a complex number. And also, according to Euler's formula, we can represent the wave in this form. This same complex number, we can represent amplitude and phase. In this case, it's going to be E naught exponential I phi. So these are all basic components we use to represent waves. And then the next thing is polarization. The polarization is described by specifying the orientation of the electric field. In this case, the electric field is oscillating along horizontal direction. If you consider this light, it is oscillating in all the direction, but once we use a polarizer, we can separate the polarized light. But when we have polarized light, it incident upon a scatterer or any particle, then we have to consider the lab coordinate. We have to consider the lab plane to get the corresponding polarization. So in this case, we can consider XZ plane, this plane. Then we can calculate the polarization, parallel polarization for that plane. This should be parallel polarization. Parallel polarization for XZ plane, which is equal to this value. And then the perpendicular polarization, which is along this y direction, it's going to be 0. But also same thing we can do for another plane, depending on our lab frame. If we consider YZ plane, then that is this plane, the polarization parallel to that plane is going to be 0. So, and then the perpendicular to that plane is going to be this value. We use negative sign to keep the right hand orientation. So now I can explain this analytical solution. This is light propagation in free space. So this case, this is the exponential I part that represents the phase. So this represents phase at any location with respect to focal point. So the phase at this location. And then electric field at length surface, we get the electric field at length surface, and we propagate everything. All electric fields are propagated toward that point, and we sum them. Integration means we sum them, and then we can obtain the electric field at any location in this area, this focal volume. So we are going to use the same theory. We are going to use the same theory for scattering of the focus beam propagation in scattering medium, but we are going to put scatterers in this area. For our case, we use spherical scatterers. So now I'm going to talk about how we deal with plane wave incident on spherical scatterers. So in this case, we have incident field. This light incident upon this spherical scatterer and generate a scattered field. The scattered field is going to scatter from the center of the spherical particle. Sometimes it's going to look like this, or it's going to be an isotropic scattering field depending on the size of the particle and depending on the wavelength. And using Mie theory, we can obtain different parameters: scattering efficiency, scattering cross-section, then far field amplitude, or amplitude component, S1 and S2. These amplitude components represent the scattering field based on the size of the scatterer. And also we can calculate the phase function. So we use all those information and develop this tool called Mie Simulator GUI. In this tool, we have different dispersion, monodisperse and polydisperse particles. And we can calculate scattering cross-section, and using that one and number density we can obtain the scattering coefficient. Then we can obtain S1 and S2, and those are the scattering amplitude component. Using that one we can calculate phase function. From phase function we can obtain G, the anisotropy. Using those two values, μs and G, we can calculate reduced scattering coefficient. So you are going to use this tool for your first exercise and the lab B. And I'm going to talk about another thing here, when diameter of sphere is much smaller than the wavelength, and diameter of sphere is much greater than wavelength. When we have a wavelength that is much greater than the diameter of sphere, we will have a single dipole, and it's going to be a uniform electric field throughout the sphere. And in that case, the scattering cross-section is inversely proportional to the fourth power of the lambda. And in other case, when diameter is much greater than lambda, we will have multiple dipoles, because at different locations the electric field is going to be different. So we have a non-uniform electric field throughout the sphere, and we have a different scattering field. Mostly in this case it's going to be forward directed propagation. And when diameter is much smaller than lambda, we can look at it in detail. We have a single dipole, and that dipole emits a field like this, and we can represent it with this kind of a donut. And in this case, the incident polarization is parallel to this screen. We can consider the parallel polarized light by cutting this section. Then it's going to look like this kind of a double sphere shape. When you cross this section, it's going to be two spheres like this way in Mie Simulator. And when we consider the perpendicular polarized light, which is perpendicular to the incident polarized light, then it's going to be a circle. So you can see this one in Mie Simulator. Okay, now the next thing is, so we have this light coming onto the spherical particle. We need to calculate the electric field, perpendicular, parallel electric field and perpendicular electric field. For that, first we have to calculate the vectorial component directed in this direction, parallel direction and perpendicular direction. So we use this kind of a transformation equation to calculate that. And then when we know the scattering field amplitude, we can obtain the scattering field at this location using this relationship. So this is the incident electric field, then this is the scattering amplitude, this gives the phase, this is the attenuation factor, because a spherical wave, once you move away from the center, you have 1 over R factor, so that will reduce the amplitude. Then we can obtain the scattering electric field parallel to this plane. Also we can do the same thing for the perpendicular field, can obtain the perpendicularly scattered electric field, this one. And we can summarize this equation like that. So we have two amplitude matrix component, S1 and S2. This is valid for spherical particle. If we consider non-spherical particles, we will have four components, S1, S2, S3 and S4. Can use same equation to calculate the electric field that is propagating away from that particle. Okay, now we talk about all the basic components, what we need to do the modeling. Do you have any questions up to here? Anything about these fundamental things in electromagnetic modeling? So we talk about the basic wave and then Maxwell's equation, the propagation polarization, and the scattering field up to now. Okay, so now we are going to use those informations for this basic model. So this is the focus beam propagation in non-scattering medium, and we are going to apply Huygens-Fresnel principle. According to Huygens-Fresnel principle, we can consider any point and then represent that point, this wave as a spherical wave propagating from that point. So we can break down this wave into multiple waves starting from that point and propagating into different directions. So we call this one as Huygens-Fresnel wavelet, or small section of secondary spherical wave. And that is the basic thing what we apply. And can see what is happening here when we represent like that. So in a non-scattering medium, when we have a HF wave traveling this way and come into the focus, all these waves are constructively interfere at this point and provide a high intensity spot. And when we take another spot, these waves propagate and provide destructive interference. So their phases are opposite to each other and provide no signal at those locations. So in this space we get the high intensity, and these spaces we get minimal signal. And so this kind of pattern we call Airy disk, and the radius from this point to first minimum is called Airy disk radius, and it is given by this equation. So this is how we apply our technique in non-scattering medium. First, we generate Huygens-Fresnel wavelet emanating from this spherical cap. So we generate uniformly distributed point from this cap and then propagate toward the center, propagate toward any location. And so we get this kind of equation. So this is the parallel electric field, this is a perpendicular electric field, and this represents the phase, and at this location we get the summation of all the parallel electric field and perpendicular electric field. After we get that one, those vectors are aligned in different directions. So we need to get everything into single plane. To do that, we consider x, y, z directions and then add the vectors. So in that way, we can obtain electric field at any location in this plane using this technique. So this is for non-scattering medium. And what we did was we compared this one with analytical solution. These are the results for analytical solution, amplitude and phase. This is our technique, amplitude and phase, and this one shows the difference. So you're going to use this tool to do focus beam simulation. So in this one, you can set the parameters and set the plane, different planes, and select electric field component, EX, EY, or EZ. And then you can run a simulation. This column only shows analytical solution, and this one shows Huygens-Fresnel approach. And so you can compare values. And you can use log values and get more detailed information. And this is incident, amplitude, and phase. The second part is now we consider there's a scatterer somewhere in this area. So how do we do that one? We use the Mie theory and calculate the scattering field for each HF wavelet. So we have HF wavelet radiating from each point. So we get the wave that is directed toward the spherical particle, and we calculate the electric field. And then we calculate the phase advance, and then we obtain the angle, scattering angle, and calculate the total scattered field using this equation what I described before. So we can obtain the scattered field and incident field. Even though there's a scattered field, incident field is propagating toward the location, and once we get those two fields, we add incident field and scattered field to obtain the total field. So in this tool, we can calculate only the scattered field. After that, we can add these two fields and get the total field. So this shows the distortion what we get from the scattering particles. We can set up two scatterers for the simulation at different locations, and then we can calculate the distortion. You can see the distortion what we get from this kind of scatterers. We have three different sizes. Okay, here are some simulation results. In this case, we put the scatterer right underneath the focus. Here we shifted the scatterer, but this is only 6 microns, this is 15 microns, and then we add another scatterer, 2 scatterers. So for each case, we can obtain the scattering field. This is using our technique, this is FDTD. And using our technique, we can get these results in like 20 minutes, 2 minutes, 2-3 minutes. And using FDTD, you have to wait a long time, like 3 weeks, if you consider the single processor. Otherwise, using multiple processors, you can get the results quicker. So we compare these results, we get the same exact results as before. And you are going to do these simulations here, so you can get you can see how fast it is. But this is for small number of scatterers. When we increase the number of scatterers and when we model the realistic situation, things are going to be complicated. So it's going to be harder and harder. Okay. So yeah, that's the last slide. So this is like a supplementary lecture to do the last 2 labs, the last lab. So it has two sections, Mie simulation and focus beam simulation. So I think I gave enough information to start working on that. If you have any questions, you can always ask. Yeah.
Do you want to tell us? Maybe you could tell us the time difference between those two lines. FDTD would be taking much more time
Yeah.
than HF-WEFS. What roughly is the comparison?
So this one probably 1 minute or 2 minutes for this simulation, because depending on the area we use for simulation, so we have to we use different resolutions. So if we need a very high resolution picture, we need to consider more a lot of points. So in that case, the time will be increased up to maybe 10 minutes. But FDTD, regardless of your resolution, you have to keep small voxels as possible for the stability. So in that case, it's going to be like 500 hours or something like that. Yeah. And also if you increase the volume, let's say you want to increase, you want to simulate a bigger volume, then it's going to be a longer time for FDTD.
Yeah. Thank you.
And also FDTD, you have to do all the simulations. You have to simulate from beginning to the end to obtain the results. But in our case, when we have a lens here, we only need to consider the interested plane or interested volume and do the simulation. So that's the advantage of this technique.
Are the color bars just a relative measurement, or is like you have these scale bars on the side, 0 to -5? Is that just a relative
This is in log scale.
log scale?
So, yeah. So those are actual values.
Oh, okay.
Yeah.